All right, so we said that there are thousands of NP-complete problems out there that people really want to solve, but that they're really difficult to solve. So what do you do when you're in the position of wanting to solve one of these problems? And let's just think for a second about, the definition of NP we said was you can solve it by brute force. So let's think about, in the real world, when is brute force not going to work? And as a benchmark for this, let's use the world's currently, as of July 2016, largest supercomputer, which is the Sunway Taihu Lite in China, which can do about 10 to the 24th operations per year. If it were running at sort of full capacity all year long, which I'm pretty sure is not what actually happens, but if it were, it could do 10 to the 24th operations per year. Okay, so let's see what happens if you have an algorithm that runs like 2 to the n, or n factorial, or even 2 to the 2 to the n. What's the largest input size n that you could solve on the world's largest supercomputer running for a year? So for 2 to the n, by the time n is 72, this becomes approximately 10 to the 24th. So you can get up to 72, which maybe is reasonable, but in reality there are lots of NP-complete problems where you're going to want to solve them for n in the thousands. And it only gets worse from there. So for n factorial, by the time n is 24, you've gotten up to around 10 to the 24th. And for something like 2 to the 2 to the n, by the time n is around 6.3, you've gotten up to 10 to the 24th. And an input of size 6 is normally something that you either think you could solve by hand or would be too small to be interesting. So the question is, when brute force isn't going to work, and in theory, sort of, that seems to be the best we know, what do you actually do? And the answer, or one answer, we'll see a few answers, one answer is you use some heuristics. So these are essentially rules of thumb that you can program into an algorithm that will help it solve many problems faster than the brute force method. They usually don't work for everything, but you don't need them to work for everything. You just need them to work for your problem. So people have obviously devoted a lot of time to this because there are problems they really want to solve, but there are a few types of problems where people have devoted more effort than others in order to really optimize them for real-world cases. So one, which we've already talked about, is SAT, where modern-day SAT solvers, and we'll put some links on the course webpage where you can find those, can solve SAT instances with something like 1 million variables and 20 million clauses or gates. Now, they can't solve all instances with 1 million variables, but they can solve lots of instances, and lots of instances that people care about, even with this many variables and gates. Another problem that people have looked into optimizing a lot is what's called clique finding. So a clique is a subgraph of a graph. You have a graph and you have a subset of the vertices where every vertex in that subset is connected to every other. So just as a quick example, so this is a clique of size 5 in this graph on 6 nodes. Okay. And in clique, the question is usually to find the largest clique you can find in a graph. And here, modern-day clique solvers can find in graphs of around 1 million nodes, they can find cliques of size roughly 500. And again, not for all graphs, but for a lot of graphs and for a lot of graphs that people care about. Another one that people have looked at a lot is called integer linear programming, where the idea here is I give you some integer matrix A and integer vector B, and you want to find integer vectors such that AX is less than or equal to B. Which means, so AX is a vector, B is a vector. This means each entry of this vector is at most each entry, the corresponding entry of this vector. Okay. This is another classic NP-complete problem. It shows up all the time in optimization. In fact, there's a whole field called operations research, whose starting point is essentially trying to come up with better heuristics for integer linear programming and its variants. And then another problem, which is even harder than this, is solving systems of polynomial equations. Solving systems of polynomial equations is actually much harder than NP-complete. It's complete for a complexity class called exponential space. And in theory, sort of the best known algorithms for this actually do take 2 to the 2 to the n time in the worst case. But again, in practice, the best known algorithms are also able to actually solve a lot of instances that people really care about. So the message here is, 1, heuristics can help frequently. But 2, if you have a problem you really want to solve, you could try your own heuristics, or you could try reducing it to one of these problems and plugging it into the sort of industrial strength solvers that exist today, because people have put a lot of effort into these. And when I say reduce, I'm talking about the same kind of problem reductions that we were looking at when we talked about NP completeness. And I should say, when you do the reducing, there's also some art to that. So for a given SAT solver, for a given piece of software that's designed to solve satisfiability, how you reduce to SAT can actually greatly affect the performance of the solver. So then, now instead of giving yourself the hard task of coming up with a better algorithm for SAT, you've sort of reduced your problem to find a reduction to SAT where the existing algorithms can work well, right? And the nice thing is the existing algorithms for SAT, or for any of these problems, often are very good at taking advantage of structure in the instances. So if you have some natural problem that you're reducing to SAT, that usually produces a very structured looking SAT instance. But again, so these things, they can take advantage of structure, they work frequently in the real world, but the real thing they rely on is that, to work well, is that the problems that arise in practice are often not worst case. But when we talk about things like P and NP and NP complete, we're talking about the worst case complexity of algorithms. So you should also be relying on that the problems that you come up with in practice are usually not going to be the worst case problem possible. And indeed, even for something like SAT, where we can solve many problems that have millions of variables and millions of gates, there are examples, even if you pick sort of examples randomly, that only have a few hundred variables and maybe a few thousand gates, where no known SAT solver knows how to solve them. And in fact, we don't know if they're solvable. We've literally never been able to solve some of these instances. But again, your problems usually aren't going to look like that.